Good morning and welcome you all for Anna University AV program, and we are going to continue with Mathematics 1 paper Unit 3. You all know what is Unit 3 is about? It is application of differential calculus. The word differential calculus, is it fears us? No, not at all. Here it is all about application of differential calculus, so you'll enjoy more about studying the application part of it. So here the unit is like, we'll start with the topic curvature and finding out the radius of curvature and different coordinates, and the circle and evolute and involute. What do you mean by this evolute and involute? You might have heard this word somewhere in your engineering graphics, I think so, where with all the angles and measurements you will be learning to draw evolute and involute. Here we will find what will be the evolute of some standard curves. We will find out there, you will learn to draw it. So this is what it has been related with your engineering graphics, and also here it is full of application part of differential calculus. The first topic itself, it is all about curvature. So we'll study different forms of curve and how are we going to find the curvature of different curves, likewise evolute and involute. Okay, so to start with, it is the unit 3 is about applications of differential calculus. You'll enjoy learning this unit. It's not completely of differentiation, so it is all about application, so you'll enjoy learning the unit 3. Applications of differential calculus. So let me consolidate the topics here. We start with curvature, radius of curvature, here we will study in Cartesian form and also in polar and also in parametric. And also in parametric form. And circle of curvature. Then evolute, involute, and then envelopes. Last topic will be envelope. So this is the order we are going to go with unit 3. Curvature, radius, circle of curvature, evolute, involute, and about envelopes. So to start with, let me define what this curvature is all about. Curvature. So it talks something about the curve. Okay, talks something about the curve. We are going to find the shape of the curve. Okay, in other words, the degree of the curve. Okay, how far it is being bended. For example, we cannot define curvature for a straight line. That will be 0. Straight line will be like this. You cannot define any curvature for this straight line. So when it is like a curve only, we can define the curvature of this curve. Let us define. Let me start with the example. Let me draw a circle. Okay, we can name this as C1, and another circle, a smaller circle, C2. We will name this as C2. You may have center and radius, etc. for each of the circle, and I am touching this at the particular point P. Let us mark this point as P. Okay. Now we have a circle. It has been all about curves. Okay. The curvature of the smaller circle will be bigger, will be greater, and then the curvature of the larger circle. So how do you say that the shape of the curve the bendness of the curve of the smaller circle will be more. When you look at the figure itself, you could be able to understand the bendness of the smaller circle will be more than the bendness of the larger circle. So that bendness we can also represent with a word called bendiness or curvedness. So the curvedness of the smaller circle will be more than the curvedness of the larger circle. So at the particular point P, how are we going to find the curvature? So this rate of bend, the shape of the curve, how far it is being like bended and it is formed like a curve, that is what we are going to find out. Okay. So now the degree of curvedness is what we are going to study. So the degree of curvedness, if that is known, then the measure of the rate of change of the curvature, rate of change of the bendness is nothing but will be the curvature. So this example will tell you like how the curvature would be in terms for a smaller circle, for a greater circle, for a larger circle. So in terms, or you can also define the curveness or bendness is more here in smaller circle than in larger circle. So we have been talking about how the curvature is all about. Let us define graphically how the curvature could be represented in terms, or how the curvature is be defined for a curve. Let me take a curve gamma. Let me take a curve gamma, and the curve I have named as gamma, and the starting place of the curve, let us take it as some A. Okay. A to B, the distance, let us take it as S, and here at the point Q, the distance could be S plus delta S. So what will be the distance between PQ is delta S. What will be the distance between PQ is delta S. Delta S. Now I am going to draw a tangent at P and tangent at Q. Take a tangent at P. This is my tangent. So let us take that touches here. Let me draw again. Axis by axis. I'm just taking a curve like this. Drawing a tangent here. Okay. And here it starts at A. This point at P, the distance we'll take it as S, and the point which touches with the other tangent we'll take it as Q, and the distance is S plus delta S. For this distance will be delta S. And the angle which makes with the tangent here, we take it as psi or phi. Tangent at the other point which meets at Q, we take it as psi plus delta psi. So the angle between the two tangents here, this is going to be delta psi. So we have taken a curve, we are going to find the rate of bendness of the curve, or we are going to define what this curvature is all about. What this curvature is all about. Okay. Now this arc distance is delta s, and the angle between the two tangents for that arc is delta psi. The rate of change of the angle with respect to the arcual distance is what the curvature is. So how do we measure that? The rate of change of the angle with respect to its arcual distance. So how do we represent that? It is by delta psi by delta s. What is this delta psi? Is the angle of contingency. That is the angle between the two tangents, where the intersection of it, as the point moves to Q, as the arc at P it moves to Q, there is a distance called delta psi. So in terms with respect to the angle and the arcual distance, if you measure, you can get what is about the curvature is. This average, getting the average of the angle with respect to the arcual distance. How do we represent that? Is delta psi by delta s. Now when you make this distance approaches to 0, that is delta psi, the small arcual distance, that delta s tends to 0, of del psi by delta s by delta psi will become d psi by ds. That as your distance delta s approaches to 0, it comes to a point. Now we are defining the curvature at the particular point P. Earlier it was like a curve, now that was the average, and here it is about the total. Now as this Q moves to P, now this delta s approaches to 0. Now we can find, or we can define the curvature at the particular point P. Now this is what the curvature is. The rate of d psi by ds. How do we write this as? The rate of change of bending of a curve at any point. That any point is nothing but the point at P. At bending of a curve with respect to its arcual distance, to its arcual distance. So that is delta s with respect to its arcual distance is called curvature. Is called curvature. So here you can define the rate of change of the angle with respect to the distance. So finding like that, you can get what would be the curvature at the particular point PS. So now we had an example saying like the bendness or the curveness. Here it is more than on the bigger circle. So here, how do we find that the curvature is? It's all about the representation of a graph, graphical representation, and how do we define curvature is? It is about the rate of change of the angle with respect to its arcual distance, that is ds. When it approaches to 0, you can very well write it as d psi by ds, or the average you can denote by delta psi by delta s. So this is what the curvature is, and it is denoted by Greek letter kappa, like this. It is denoted by a Greek letter called kappa. So kappa is your d psi by ds, or in other words, it is the measure of the curvedness or the measure of the bentness of a curve is nothing but the curvature is. Okay. So the curvature is over. Now we have defined the curvature. Let us define what will be the radius of curvature will be. So if this is the curvature, that is d psi by ds, if this is a curvature for this particular curve at the point P, when you take the reciprocal of the curvature, we can define it for radius of curvature. So the radius of curvature is defined as reciprocal of the curvature. Radius of curvature is defined as reciprocal of curvature. One fine example I can give you where the roller coaster, where in great amusement parks they will have roller coaster where we will enjoy going a ride in a roller coaster. So if you see that marks where the roller coaster is been rolling about, the curves, the track will be like this, will be shaped like this. Only then it will move with ups and downs, you will enjoy a lot. If it is in form of this shape where it will go and stop here and you may not have that much continuation to carry that train or the roller coaster is moving about. Therefore, if you know the curvature, the rate of the bendness of the curve, if it is being defined like this and it is being fixed in the form of the curves with same curvature, so that the roller coaster, it is being moving about this way, we will have a good enjoyment than it is in the shape of a square or a rectangle. So here where it is one part of the application, you can see where directly the curvature is applied. So the rate of bendness of the curve, it is measured and it is being placed over there. Only then it goes on with like the curves, and whereas here you cannot find that. So this is what one application where I can tell you. Okay. The radius of curvature form as we define what is a radius of curvature. Radius of curvature is a reciprocal of curvature. Okay. Reciprocal of curvature. The radius of curvature notation is rho, and as we say it is reciprocal, it is 1 by kappa. Okay. 1 by kappa is nothing but ds by d psi. Okay. 1 by kappa is d psi by ds. This is what the rho is. So what is the relation between radius of curvature and curvature is? What could be the relation between radius of curvature and the curvature? Is they are reciprocal to each other, inversely proportional. So kappa is 1 by rho or rho is 1 by kappa. This is what the relation is about radius of curvature. We have radius of curvature in two different forms. One is Cartesian. How do we find the radius of curvature for any Cartesianary curve? Cartesian form. The other is polar form. Parametric form. So let me first do all about Cartesian form. Once that is over, we will take care of the parametric form of the radius of curvature, and then we will do some problems over there. Here, when the Cartesian curve, how do we represent the Cartesianary curve? As y as a function of x. If you have a curve in terms of y as a function of x, then we can find the radius of curvature rho with the formula rho is equal to 1 plus dy by dx whole square to the power 3 by 2 by d square by y dx square. This is a formula which is derived to find the radius of curvature in the Cartesian form. What will be dy by dx? It is the first order derivative of the curve, and d square y by dx square is the second order derivative of the curve. And using this formula we can find the radius of curvature for any curve. Therefore, we can find the radius of curvature provided that is in the Cartesian form. If it is a parametric form, we will have in terms of the parametric equation. Okay, that we will do it later once we finish first we'll finish the Cartesian form. Okay. If the curve it is in the form of y equal to f of x, this is my radius of curvature. If at all my curve is represented in the form of x is equal to f of y, then what will be the cases? Radius of curvature can be defined in the form 1 plus dx by dy whole square to the power 3 by 2 by d square x by dy square. So this formula we may use. Usually we go with the form y equal to f of x. If that fails, then we will take the radius of curvature in the form for the curve x is equal to f of y. If that radius of curvature formula here it fails, therefore we can use this particular formula by taking the Cartesian curve as x is equal to f of y. Here, this could also be, what is this dy by dx could be written as this form. You can also mention it as 1 plus y1. y1 stands for dy by dx. So y1 square by y2, and this is to the power 3 by 2. This is what the radius of curvature rho is above. y1 is dy by dx and y2 is d square y by dx square, where y1 is dy by dx and y2 is d square y by dx square. So in short, you can very well write the formula rho as 1 plus y1 square to the power 3 by 2 by y2. So with this formula will help you to find the radius of curvature for any curve. And here, if the curve, that particular formula fails, you can use this formula to find the radius of curvature. We will solve some problems. So let us take some random curves and we'll find radius of curvature for those curves. Maybe the curvature at the particular point it is defined. So we'll be having problems defined to find the radius of curvature at the point. Okay. So the first problem. Find the radius of curvature for the curve y is equal to e power x. We are going to find the radius of curvature for the curve y is equal to e power x at x is equal to 0. We are going to find radius of curvature at the point at x is equal to 0. Okay. Now, if x is equal to 0, it means that y is equal to 1. So here it is mentioned about x 0. It is understood what is the value of y is. What is radius of curvature formula is 1 plus, it is a Cartesian curve, y is expressed as a function of x, 1 plus y1 square by y2, and it is 1 by y1 square to the power 3 by 2. Let us define what is y1, let us find what is y1 and y2. How do you find y1 by knowing y? We differentiate. We can take this as first equation. Differentiate first equation with respect to x. So what do you have? dy by dx, or you can very well write this as y1. y1 is equal to e power x differentiation is e power x. We also find the functional value of y1 at x is equal to 0, because we are going to find the radius of curvature at the point, at the particular point. So y1 at x is equal to 0 will be e power 0, that is 1. So y1 value will be 1. Then we differentiate again differentiating with respect to x. Already I differentiate once, again we will differentiate, that will be y2 e power x, differentiation is e power x again. So here this is what differentiated again. This is what differentiate. E power x is again differentiated. So you get e power x. Now y2 at the point x is equal to 0 is e power 0. So y2 is also 1. Now as we substitute in radius of curvature rho, that is 1 plus y1 value is 1 square to the power 3 by 2 by 1. So rho is equal to 2 to the power, or you can write rho is equal to 2 root 2. This is what the radius of curvature for the curve y is equal to e power x. Y is equal to e power x at x is equal to 0. So this is all about how do we find the radius of curvature. So in order to start with, I have taken a very simple problem. So let us solve some more important problems in this topic. Okay. The next question is, let me take a different function. Earlier it was an exponential. Let me try some trigonometric function. Find the radius of curvature. We are finding the radius of curvature for the curve y is equal to 4 sin x minus sin 2x at x is equal to pi by 2. We have a curve. So if you trace a curve, you can even draw. We are not going to draw all the curve. You find the radius of curvature. 4 sin x minus sin 2x at the point x is equal to pi by 2. Right. Now, what is the formula? 1 plus y1 square to the power 3 by 2 by y2. So let us find y1. You can name the given curve as first equation and differentiating first with respect to x. So what you get is y will become y1. y1 is equal to 4 cos x. 4 is constant. Differentiation of sine is cos minus cos 2x into 2. This is multiplied with 2. Now y1 at x is equal to pi by 4. That is what we require. X is equal to pi by 2. Functional value at the derivative y1. So it is 4 cos pi by 2 minus 2 cos 2 into pi by 2. Now, what is the value you will get? y1 at x is equal to pi by 2 is 4 cos pi by 2 minus 4 cos pi by 2 minus 2 cos pi. 2 gets cancelled, so it's cos pi. So 4 cos pi by 2 is 0 minus 2 cos pi is 1. It is minus 1. So we have is plus 2. y1 is plus 2. Again, differentiating the first equation. Again differentiating y1, we will get the second order derivative, that is y2. Earlier what we had, so it is 4 is constant. Again when you differentiate cos, you will get sine minus sine x minus. Again we have a minus sign, so it is plus. Already we have a 2, so it is plus 4 sine 2x. See, it is 4 when different constant, 4 is constant, cos it is minus sin x, minus 2 is a constant, and differentiate this sin 2x into 2. So that is what the plus sign is. Now y2 at x is equal to 5 by 2 is 4 sine 5 by 2 plus 4 sine 2 times of 5 by 2. This gets cancelled. So 4 times of sine 5 by 2 value is 1. And here you will get 2 gets cancelled, sine pi is 0. So that is 0. So y2 value is 4. y2, the constant value of derivative y2 at x is equal to 5 by 2 is 4. So let us all substitute this in the formula. Rho is equal to 1 plus, what is the value of y1 we calculated? It is 2. So it is 2 square to the power 3 by 2 divided by 4. So it is 1 plus 4 to the power 3 by 2 by 4. All this is 5 to the power 3 by 2 by 4, or rho is equal to 5 root 5 by 4 is the radius of curvature for the curve y is equal to 4 sin x minus sin 2x. Some more important problems we'll do. Hope the procedure is clear. We do find what is y1 at the value at the point and y2 at the point, and by substituting this in the radius of curvature formula we can find what is the radius of curvature for the curve, Cartesian curve. The third problem is about y is equal to log cos h x by c. Y is equal to log cos h x by c. We are going to prove the radius of curvature for this Cartesian curve at the point x comma y. Earlier I mentioned what is the point. Here for any particular point. For any particular point in general, so that is about x comma y. We are going to prove this is y square by c, and also we are going to find what is the value of rho at 0 comma c. We are going to do two things here. One is we are going to prove the radius of curvature of this curve at x comma y is y square by c, and we also find rho at the point 0 comma c. One specification, one point which is specified, the other point is in general, that is x comma y. Okay. We can name this as number 1. We know what is the radius of curvature formula. Let us differentiate and find y1. We differentiate first equation with respect to y1. So what is the logarithmic differentiation? Log of cos hx will be 1 by cos hx by c. We have to differentiate this part. We have just differentiated log, and now we are differentiating what is cos. Now as we differentiate this, you will get minus sin x by c. Okay, differentiation of, here it is hyperbolic function, so it is not a negative sign, it is plus. As we differentiate hyperbolic function, differentiation of cos will also be plus sign. Differentiation of cos will also be plus sign. So sin hx by c, differentiating the angle, you will have one more, that is 1 by c. This is what your y1 is. Therefore, y1 is equal to once again I will check the question. I have listed the problems which you are going to do from this topic. So it is just c cos hx by c. If we proceed with this curve, we can prove y square by c. Maybe the log we can do it with we can do it as a next problem. It's just y is equal to c cos hx by c. So I'll do the necessary correction there. It is not log. If we do it with log, we may not get the radius of curvature as y square by c. We can do that as separate request. Yes. It is just c log. So we'll add the it's just c log hx by c. So y1 will be c. So differentiation of cos will be sin hx by c. Sin hx by c, and the differentiation is again 1 by c. This gets cancelled. So y1 will be sin hx by c. This is what your y1 at any point x comma y is. y1 at any point x comma y is. Now we have to differentiate this again to find y2. Differentiation of sine will be cos. So hyperbolic function sin hx is cos hx by c into angle differentiation is 1 by c. So this is same as y2 at the point x comma y is. So let us substitute that in rho. Rho is equal to 1 plus y1 square to the power 3 by 2 by y2, where this is 1 plus, what is y1? Sin hx by c whole square to the power 3 by 2 by y2 is cos hx by c into 1 by c. You should not multiply with this. This is separate. It is angle and it is a constant. So now as we simplify, 1 plus sin h squared x by c divided by to the power 3 by 2, and it is cos h x by c into c. We write it as sin square hx sin square. Now this is equal to, as we square that, you can write it as cos square hx by cos square to the power 3 by 2 by c cos hx by c. This is the product where it is c, it is not in the denominator, it is in the numerator. See, the c is the denominator and we have the denominator, so that will be the numerator. You can carry this c here, c. So now as we simplify further, it is cos cube hx by cos hx by x by c into c. Now this is c cos square h x by c. Now what is the Cartesian curve is about? Y is equal to c cos hx by c. So we can write this as c, since we have y is equal to c cos h x by c. Now y by c you can very well write it as cos h x by c. So now this could be written as y square by c square. Am I right? This whole square here, it is y square by c square. So at last c gets cancelled, so you get y square by c is rho, which is the radius of curvature at the point x comma y is. So we have proved the radius of curvature at any particular point x comma y for the Cartesian curve y is equal to c cos hx by c is y square by c. Now also there is added one thing which is added in the question. We also have to find We also have to find what is rho at a comma 0, c comma 0 comma c. Sorry. So I have to find what is rho at 0 comma c. What is rho actually? It is y square by c. It is y square by c. What will be rho at 0 comma c? Is c square by c. So rho is equal to c at 0 comma c. So what is the value of rho at 0 comma c is as a constant. It's a constant, that is c. Okay. So this is how where you can find it for a particular any particular point, any point that is x, y, and you can make it for a particular point 0 comma c2. Right. Next problem is we are going to find the measure of curvature. What do you mean by measure of curvature is we are going to measure the curvature, measurement of the curvature. Earlier it was like radius of curvature. Now the measure of curvature is what is the relation between the curvature and the radius of curvature? That is reciprocal of the curvature is radius of curvature. So as we find the radius of curvature, we can give the measure of curvature as reciprocal of it. So let us do one problem in this. We are going to prove that, we are going to show that the measure of curvature, we are going to show that or prove that the measure of curvature of the curve root of x by a less root of square root of y by b is equal to 1. We are going to find the curvature for this curve at the particular point, at any point x comma y is 2 times of ax less by to the power 3 by 2 by ab. This is what we are going to prove about for this curve. We are going to get the measure of curvature at x comma y is this. Okay, so let us start working out. So we'll find what will be the usual steps we will do it. We find we check whether it is a Cartesian curve because we are doing problems in Cartesian. Parametric is also there, so we'll do that separately. We'll differentiate this with respect to x, and also we differentiate with respect to y. Here it is a general point x comma y, and finally we're going to check whether we will be able to get this as our radius measure of curvature is. We can write the curve as root of x by root a less root y by root v is equal to 1. Now differentiating this with respect to x with respect to x, what do you get? 1 by root a is constant. What's the differentiation of root x is? It is 1 by 2 root x plus differentiation of y is 1 by root v is constant, 1 by 2 root y into dy by dx is equal to 0. Now what will be my dy by dx is, you can calculate from this. One by root b take the first term to the other side, it is minus 1 by root a into 2 root x, or if you want dy by dx is minus 2 root b root y by 2 root a root x. This gets cancelled. Root b root y into root a root x. There. This is what your y1 is. This is what your y1 is all about, dy by dx, or we call it as y1. Let us take this and differentiate again with respect to y. Now this is y1 at the point x, y. Let's find y2. So as we find y2, root b by root a will be constant. Root y and root x, how do you differentiate? By u by v method we have to differentiate. So that is y2 is equal to root b. We will take the negative sign also, constant. So as we differentiate this root x whole square, what is the formula? V u dash minus v u dash minus u v dash by v square. So v square is root x 1 by 2 root y into dy by dx, that you can give it as y1 minus u is root y into 1 by 2 root x is, which is equal to minus root b by root a x. Now this is root x by 2 root y. What is the value of y1 we found earlier? It is just minus root b by root a root y into root x minus root b by root a into root y by root x. This is what the y1 we found. So let us substitute and simplify. Minus root y by 2 root x. As we simplify this further, minus root b by root a. Now this root x gets cancelled. Minus root y gets cancelled. Minus root b by 2 root a minus root y by 2 root x by x. Now let us take LCM, and this is minus, we can also take a negative sign out, so it becomes plus root b by x root a. I am just carrying this x here, it's all about denominator. And here taking LCM, you get root x root b minus root y root a divided by root a root x. It's plus. I have taken the negative sign out. Negative is a common I have taken, so minus into minus plus. This x I have carried here. Now taking LCM for this, 1 by 2, 1 by 2, this 2 also you can take it out. 1 by 2, that is common. Now, what is your y2 is? Root b by 2 root x, it's just x root b, is a root a x, and here we have root x root b plus root y root a divided by root x root a divided by root a root x, that is root x root a. Okay. Now this part is, you can rewrite from the curve. What is a curve? Root x by root a. This is what a curve is. By root y by root b is equal to 1. As we take LCM here, we can write this as root x root b plus root a root y by root of ab, or root a root b is equal to 1. As we cross multiply, see, you can take this root x root b plus root y root a root a in the form of root ab. See, you can replace this, the numerator part, you can give it as root of ab. So that is what I am going to do here. So root b by 2 root a into x. Numerator is root a root b by all, it is product root x into root a. Now we cancel out all the possible terms. Root a gets cancelled. This is b divided by 2 root a x into root x. This is what your y2 is. We've got the simplified form of y2. Earlier we found what is y1 and now we got what is y2. Now let us substitute in the radius of curvature formula. Rho is equal to 1 plus y1 square by to the power 3 by 2. Okay. 1 plus, what is y1? Root b root y by root a root x. Root b minus of root y by root a root x whole square to the power 3 by 2 by, what is y2? b by 2 root a x into root x. b by 2 root a x into root x. b by 2 root a x into root x. Let us simplify this further. As we square, and it's 1 plus by ax to the power 3 by 2 by b by 2 root of a x into root x, which is equal to, why don't we take LCM there in the numerator? It is ax plus by by ax to the power 3 by 2 into reciprocal of this denominator to the denominator. You can write it reciprocally as 2 root a x into root x by b. Now you can write the numerator as ax plus by to the power 3 by 2 and the denominator x as ax to the power 3 by 2. Into 2 root a x into root x by y by b by b. So just check. So this I have written separately, this part separately, and 2 root of a x into root x and by b. Yes. And further simplifying, this is ax plus by to the power 3 by 2 into 2 root a x root x into x by, this is ax into root a root x into b. This gets cancelled, so we get 2 times of ax plus by to the power 3 by 2 by ab. So we have proved the radius of curvature rho as 2 times of ax plus by to the power 3 by 2 by ab. This is what the radius of curvature is. Measure of curvature, as we discussed here as measure of curvature, then this will be reciprocal. This will be reciprocally given. If it is measure of curvature, then it is ab by 2 times of ax plus by to the power 3 by 2. This is actually rho, and the reciprocal of that will be measure of curvature. Therefore, if this is radius of curvature, measure of curvature rho kappa is 1 by rho, so it is 1 by 2 times of ax plus by to the power 3 by 2 by ab is equal to ab by 2 times of ax plus by to the power 3 by 2. This is what the measure of curvature is. Reciprocal of that. This is again one of a different and typical problem, and it is in a way point of examination. It is important too. Okay. Now we found the radius of curvature for 3 different curves, and one problem where the measure of curvature we found. Okay. Now let us take a simple question like finding the radius of curvature for x square plus y square is equal to 25. Okay. What is this equation is about? What is this equation is about? It is a circle equation. It's a circle equation where what could be the center? Center is 0, 0 and the radius is 5. How are we going to find rho for this? Find rho. Usually what do we do for any Cartesian curve? We find the derivative y1 and y2, and that in the radius of curvature, taking it as rho is equal to 1 plus y1 square to the power 3 by 2. By y2 we will find what is radius of curvature. And here if you do find that way, you will find rho. But then looking at the equation, we could say it is a circle equation. Okay. Now we have one property where radius of the circle is nothing but the radius of the curvature. So this property we are going to use. Radius of curvature is nothing but radius of the circle. Now what is the radius of the circle which is given here? The radius is 5. Okay, because of 25 it is given as 25. So 5 square is 25, radius is 5. So if the radius of the circle is 5, then the radius of curvature will also be 5. That's all. So using this property we can straight away find what is rho. We found rho, that is 5, because we have a property like radius of circle is, again it is equal to radius of a curvature. Do we have any curvature for straight line? Definitely no. So there is no curvature for straight line, and you have one more property saying that radius of circle is the radius of curvature. One more problem where if you have like x squared plus y squared minus 2x plus 4y plus 1 is equal to 0. Find rho for this curve. How do we find rho? How are we going to find rho for this curve? This equation, the curve equation, it is a circle equation. X square plus y square minus coefficient of x minus coefficient of y, this is y, plus a constant is equal to 0. So just now we went over property saying radius of the circle is nothing but radius of curvature. So if you could find the radius of the circle, and therefore the radius of curvature is known. Now how do you find the radius of the circle? By knowing the center and by calculating with the radius formula. So how do we find the center? Minus half coefficient of x, that is 1, minus half coefficient of y, that is minus half coefficient of y, that is minus 2. This is what the center is. And how do we calculate radius? Root of this 1 square plus minus 2 square minus t, minus constant, that is minus 1. So which is equal to root of 1 plus 4 plus 1. So the radius of the circle is root 6. Therefore radius of the curvature is also root 6. Since r is root 6, rho is also root 6. So this is how you can expect doing problems if it is a circle equation. So we have done some few problems in Cartesian curve. In the next session we will do problems with the parametric form. So these are the two forms where you do the radius of curvature. There are different forms. You can also do it in implicit form and polar form. So as of now, here we will do only Cartesian and parametric. Only Cartesian and the parametric. So the Cartesian problems are all over. We'll do some more problems in parametric by introducing how do we get the parametric form of the radius of curvature in the next session. And thank you for patiently listening. Thank you.